All right, one of the most important things that we do in statistics, especially in applications, is being able to simulate random variables. And the way that we do it, or the theoretical justification for it, comes from the inverse probability transforms that we showed in the previous video. So these are called inverse probability transforms. And what we're doing is we're specifically working with, on the one hand, we can always get a uniform random variable from any random variable just by processing the random variable through its distribution function. That's the first part. And then the second part is we can always get any random variable from its distribution function from a uniform distribution by processing it through the inverse of the distribution function, as we saw above. So let's see how this works in practice. And I'm actually going to show it in the case of a discrete random variable. Suppose X is a discrete random variable. With a probability mass function given by takes values 1, 2, 3, or 4 with probability 0.1, 0.3, 0.2, 0.4 respectively. Okay. So let's plot the cumulative distribution of X. So the cumulative probabilities are like this. So at 1, we take the value 0.1, so it's 0. Well, it's 0.1, then we have to jump up to 0.4, right? By 0.3, we jump up at 2, and then we jump up by 0.2 to 0.6 at 3, and then we jump up to 1 at 4. And in between, we are flat. This is the distribution function. And let me just highlight it here because it's 0 to the left. And then, all right. So now what we want to do is we want to say, okay, given a uniform, how do we simulate? And what we need to do is we need to define a function g from uniform interval 0 to 1 to the values that X can take, such that these have the right probabilities, right? That G of U has the probability that G of U is equal to little x is equal to the mass function of X for all X. And the way that we do this is we're going to define it in this way. We're going to say, let's define G of U to be 1, 2, 3, or 4 based on, we're going to generate a uniform, we're thinking about generating a uniform random variable up here, and we need the probability that the uniform equals a certain value to be equal to the mass, the probability mass function. So what we can actually do is drop a vertical line in each of these steps. And what we do is we just kind of trace over and look, where does this hit the function? It hits it right there. Once it hits it, we drop it down. Okay. And so what that means is that we're gonna define G in terms of the kind of the pseudo inverse of F. And when we do this, we realize that, okay, if we look at it this way, probability that G of U, for example, is equal to 3. Well, G of U is equal to 3, provided that U is between 0.4 and 0.6, which for a uniform random variable is 0.2. And if we look up, we see that that's exactly what the probability needs to be in the mass function of X. So this is how simulation can get done in practice. In particular, we think of inverting the CDF, and we could still invert CDF for discrete random variables just by doing this step function, dropping the verticals as we saw here. More generally, if we do have a continuous distribution function, we can just invert it because the flat spots can never get hit here, as you can see. Because if we were to fall right on 0.6, theoretically, we would first run into it at this value here, which would give us the 3. There's no way for us to get anything in between 3 and 4 because that horizontal step cannot possibly get hit when we draw when we draw the horizontal to go and see where this corresponds to. So this is a way to simulate discrete random variables. Same thing applies for simulating continuous random variables, and really it is an application of what we've already learned here in terms of the inverse probability transforms using the distribution function and its inverse and applying it to a uniform random variable. So going back to a previous class when I said that the uniform distribution is in many ways the most fundamental and important distribution in probability, and then from there where we constructed uniform variables from Bernoulli random variables, that the Bernoulli random variable is fundamental. This is why. It's because from those ingredients we can, in principle, and in a very concrete sense, generate an instance of any random variable that we might be interested in.